Hello, welcome to this new mathematics video, again still on the subject of ordinary differential equations. Now in this particular video we're going to look at Hermite's differential equation as written here in equation 1. Now this is a second order linear ordinary differential equation, but you'll notice that it not only has a variable coefficient in front of the second term here, so in front of the first derivative, as it were, but it's actually got a coefficient of 2n. Now n can take the values 0, 1, 2, 3, and in fact you can have any positive value for n that you need or require, providing, as I said, it's positive. So you can't have negative values of n and you can't have fractional values of n. And the reason for that is that the first linearly independent solution to equation 1 is obtained from this formula here. And as you can see, you have to calculate the nth derivative. So n can only be positive whole integers. You can't have negative integers or fractional um, uh, um, numbers or whatever. So that's how you deal with the Hermite differential equation. You find the value of n, and then you plug the value of n into this formula, and out pops your first linearly independent solution, which will solve that equation. But you have to know what n is, and we're going to look at, I think we'll look at the three first types of Hermite differential equation. So again, I've written the equation down there in equation 1. It's what we had on the previous page. So that's just there for reference. Now, when n equals 0, this term here in equation 1 disappears. So we're just left with d squared y by dx squared minus 2x dy by dx equal to 0. When n is equal to 1, this term here, this third term, becomes 2 times 1y. So we've got a 2y term here. And indeed, equation 3 reads d squared y by dx squared minus 2x dy by dx plus 2y equals 0. And when n is equal to 2, then you've got 2 times 2 here, which is 4. So equation 4 reads d squared y by dx squared minus 2x dy by dx plus 4y equals 0. Now, if you were in any situation really, or a test or an examination, and you were given an ordinary differential equation to solve, if it were a Hermite differential equation, you would have to recognize it as such. If you would probably be told what it was, but what you would have to do, you would have to observe that the term, and I'll just bring this in red. So you would have to recognize that this term is the 2n term. This term here is the 2n term. There, of course, it's just 0. But ideally, that's what you would do. You would recognize that 2 is equal to 2n and then work n out from that. 2n is equal to 4 in equation 4, so you would work n out to be equal to 2 in that. And so I think we'll go on to the next page. So, for example, with this example of a Hermite ordinary differential equation, we've got d squared y by dx squared minus 2x dy by dx plus 8y equals 0. And as you can see, I'll ring this in green. This is the 2n term there. 2n equals 8. So from that, you can quite easily work out that n is equal to 4. So the first linearly independent solution is obtained by substituting n equals 4 into the formula for the first linearly independent solution. I really actually should have given that a label. Let me just see. Yeah, I've already labelled the other equations now. So anyway, you substitute n equals 4 into that general first linearly independent solution. What we're going to do is we're actually going to find the general solution of equation 5 here. So what do? Well, we have to recognise that 2n equals 2. So that implies that n equals 1. It's just a simple equation that you solve, and n turns out to be 1. So y double prime minus 2xy prime plus 2y equals 0 is a Hermite ordinary differential equation with n equal to 1 here. So the first, and I'll write this down, the first linearly independent solution is therefore and we'll write down the solution in red. So we've got y equals, well, we've got minus 1 to the power. I'm going to write the actual general first linearly independent solution down with n in it. So we've got e to the x squared there times dn by dx to the n of e to the minus x squared. Right? So as I said, n is equal to 1. So basically what we do is we substitute, we just erase that. So what we do is we substitute n equals 1 in for n in that equation, in that solution. So actually we don't need to write the ones here in the derivative part, the index of ones. We can just leave those out. So as you can see, we've just got a first derivative. So if we go on to the next page, then what we have, if I just change back to black, is y equals, I'll write it all down again, minus 1 to the 1, e to the x squared times d by dx of e to the minus x squared, right? So that quite literally and quite simply comes out to be, well, you've got a minus 1 to the power 1, which is minus 1, times e to the x squared there, that doesn't change, times the derivative of this in brackets. So if I just outline this there, we find the derivative of that. Well, the derivative of that is just, first of all, the derivative of the part in the exponent, in the power part of this exponential, which is minus 2x. So that's multiplied by minus 2x times e to the minus x squared. And that is how you find the derivative of that, and therefore find the whole first linearly independent solution. And we can tidy that up and we find that y is equal to, well, we've got minus times a minus, which is a plus. So we've got plus 2x, and we've got e to the x squared times e to the minus x squared. And that just comes out to be 2x e. Well, x squared minus x squared is 0. So the solution is 2x. That is our first linearly independent solution for the case when n equals 1. And I'll just write it there for you. So y equals 2x is the first linearly independent solution to the Hermite equation when n equals 1. Right? But there's a general solution we can find. And so this isn't the end of the story. You might recall from previous videos of mine that to find the second linearly independent solution, then y2, that is the second linearly independent solution, is equal to y1 times, in square brackets, the integral of e to the minus the integral of p dx, all divided by y1 squared, dx, plus, I'm putting the constant in now because I usually forget to put it in normally. I don't want to do that on this occasion. So basically, y2 is equal to y1 times, in brackets, the integral of e to the minus integral of p dx divided by y1 squared dx plus c. Well, you may remember from my previous videos how to find p. So what is p? Well, we have to go back to the original equations. So basically, I'll write this. I'll write this down in green. So the original equation was y double prime minus 2x y prime plus 2y equals 0. Right. Now, if you've seen my previous videos, you'll recognize that that is equal to p. That second variable term, including its sign, which is a minus sign. So minus 2x. Okay? So, we also know, well, we'll write that down first. So p equals minus 2x. And we also know that y1 is equal to 2x. These are not the same thing, but they look similar. So don't get them confused. So let's go on to the next page because we have to substitute these values into this second linearly independent solution. And in fact, I'll give it a label. Let me see. We'll call that equation 7. Right. Okay. So let's go on to the next slide. So we've got y2 equals, I'm going to write this down again so that we can see it for reference. E to the minus the integral of p dx over y1 squared dx plus c. And we know that y1 is 2x. So we put 2x in there, multiplied by, in the square brackets, the integral of e to the minus the integral of minus 2x dx over plus 2x. So it's 2x squared. 2x squared. Remember, that's y1 there. Let me just make that a little clearer. Right, let's y1 squared. So y1 y1 was equal to 2x, because we've just worked that out, and p was equal to minus 2x, right? And we've substituted them all into there. Now, we haven't quite finished, because that's a dx, and that's still a constant. Now, we have to simplify all of this expression. Let me have a look. So we'll call that equation 8. Right? Equation 8. So equation 8 simplifies to give y2 equals 2x times the integral of e to the integral of 2x dx. You see the two minuses multiply together to give a plus, and that's divided by, we want to write that down as 4x squared. So we've got the integral of e to the integral of 2x dx divided by 4x squared, and then we've got a dx term there plus c. Right? Now, we're going to simplify that a bit more. So we've got y2 equals 2x multiplied by e to the integral. Well, if you remember, that's the integral of 2x. So the integral of 2x dx is just simply x squared. So we can just write down x squared there. If I can just erase that. X squared, right? So we'll just go back. So the integral of 2x dx is just x squared, and we're dividing that by 4x squared. Oh, there's an integral sign in there. That's important. Put the dx there, plus c. Let me see. So we'll call that, and I'll label it in red, equation 9. Is that right? Yeah. So equation 9. Now, equation 9 is very difficult to solve if you're doing it by hand. In fact, you've got to write it out in terms of error functions. So if you use a mathematics package to work out the integral of this part here, so the integral of e of x squared all divided by 4x squared, then again, ideally you would use a mathematical package for speed, but it would otherwise be very difficult to work out at longhand. And I'm just going to write down what this integral actually is. So I'll write it down in, I'll write part of it down in black ink, if I can get the colours right. So we've got y2 is equal to 2x times, in brackets, we've got the integral of e of x squared, e to the x squared rather, or divided by 4x squared dx. And that comes out to be equal to 1/4 times, in brackets, the root of pi times the imaginary error function of x minus x squared over x. And we've also got this constant. There, we mustn't forget that. So we've got our constant. Now, that's what that is. You can simplify that a little bit more if you want. Let's, well, can we simplify it really in any meaningful way? We could multiply things out. So we've got y2 equals, well, 2x times a quarter is just x over 2 times root pi times the imaginary error function of x minus e to the x squared over x, close bracket, plus, well, that constant there, so this constant here gets multiplied by the 2x there. So we will write that in green, so we get 2cx. Right? Now, that is our second linearly independent solution. We found it. So the general solution, let's write this down. So the general is y equal, so the general solution is y equals y1 plus y2. So y is equal to, well, you know what the first linearly independent solution was? That is y1. y1 is 2x. So if we just write that down in place of y1, we've got 2x plus y2. Well, y2 is this term here. So what I'm going to do is I'm going to see if, no, I can't, I don't know how to cut and paste that, but we'll write it down the longhand hard way, as it were. So that's plus x over 2 times pi, imaginary error function of x, minus ex squared over x plus 2cx. But hey, look, this 2x and the 2cx up here combine. This nearly always happens when you're adding two linearly independent solutions together. The second linearly independent solution has a component that will add quite nicely to the first linearly independent solution. And that indeed happens here. So we've got y equals 2x plus 2cx plus x over 2 times, let me get this right, I'm rushing a bit here, aren't I? Let's make this look a little neater. X over 2 times, in brackets, the root of pi, error function, there we are, minus e to minus x squared over x. Oh dear, that's not really very, right, there we are. There. It's a little bit better. Now, the thing is, we want to write this component underlined in red. We want to just underline that as, just one component. So the general solution is written as y equals ax plus bx over 2, and I'm going to have to look at this, times root of pi, imaginary error function just write that a little more neatly. Minus e to the x squared over x. Right, and that is the solution. That is the first linearly independent solution when to Hermite's ordinary differential equation when n equals 1. And that is basically that. So I hope you've enjoyed that video and got something out of it. For now, I'll say goodbye and hope to see you in the next video. So cheerio for now. Okay, bye.